Hey everybody, today we'll be discussing the photoelectric effect, which is a crucial foundation in quantum physics. Firstly, the photoelectric effect is emission of electrons from a surface, and it's usually a metal surface, when the surface is irradiated by UV light. So this is depicted by this visual right here, where we have light rays coming into a metal surface and the electrons are emitted once the light rays go through the surface. Furthermore, each metal has a characteristic energy barrier for an injection of an electron, and this is known as the work function, represented by this symbol right here. Thus, only radiation with a quanta of energy that exceeds the work function can liberate electrons. Since we know energy is given as E equals hf from the particle nature of light, this means for electrons to be ejected, we need to have energy greater than the work function, or in other words, hf greater than the work function, because energy and hf are equal. To find the maximum kinetic energy of electrons, you can apply this crucial equation right here, which is half mv squared is equal to hf minus the work function. To continue, 3 experimental observations of the photoelectric effect found were: Number 1, no electrons are ejected unless frequency of radiation exceeds threshold frequency value of the metal. Number 2, once threshold frequency is exceeded, the kinetic energy of the electrons ejected is proportional to the frequency of the incident radiation. And the third observation found in the experiment for the photoelectric effect was the kinetic energy of ejected electrons does not depend on the intensity of the incident radiation. It only depends on the number of electrons ejected. That's what intensity depends on. Let's now look at one practice example applying what we have learnt. So the practice example we have here is the work function of rubidium is 2.09 electron volts. Can blue 470 nanometers light eject electrons from this metal? Firstly, we identify that for electrons to be ejected, hf must exceed the work function. Next, we can apply E equals hf to find the energy, since we know frequency is equal to speed of light divided by wavelength. That means E is equal to hc over lambda, which is wavelength. Lambda is wavelength. We know h is Planck's constant, given as 6.626 times 10 to the power of negative 34 joules seconds. C its speed of light, given as 3 times 10 to the power of 8 meters per second, and lambda is the wavelength given in the question as 470 nm, which is in meters 470 times 10 to the power of negative 9 meters. And this conversion is required so that all variables are in SI units, Standard International Units. Next, substituting in the gathered data, we get E is equal to, so we've just plugged in all these values into this formula, so all these data into that formula. Once we do that, that yields an energy of 4.23 times 10 to the negative 19 joules. Next, we must convert this to electron volts so that we compare the energy with the provided work function of rubidium of 2.09 electron volts. Thus, to convert our answer from joules to electron volts, what we do is we divide it by 1.6 times 10 to the negative 19. So that's the working out right there. And that yields 2.64 electron volts. Finally, 2.64 electron volts does exceed 2.09 electron volts. Therefore, hf, which is 2.64, does exceed our work function. As a result, blue light cannot eject electrons from this metal, which is the final answer. I hope this video on introducing the photoelectric effect was useful in building your understanding on this topic. Thanks for watching. I'll see you guys later.